Right, here we go with our next section. This is 5.7 applications of exponential functions. So in the last couple lessons, we did a lot of work with logarithms and log laws and swapping back and forth between exponential form and logarithmic form. Now we're going to start off in 5.7. This is going to be applications of exponential functions. When we get into 5.8, it'll be applications of logarithmic. So following a logical order with this. But we'll start off with this. And we've kind of talked about this a little bit before, some of this idea of exponential growth and decay. So it starts off by saying, okay, so if we have this function in the form y is equal to a times c, if c is greater than 1, and that's a critical part of this, is looking at the base of your exponential. And sometimes it's called b, and in this case, it's being called c, but regardless. If it's greater than 1, it's going to be growing because you're multiplying. Your initial amount of a times this c a certain number of times, depending on what x is. And if it's greater than 1, it'll be growing. If it's between 0 and 1, our value will be declining, and it's called decay. And so there's two forms of c. Between 0 and 1 is decay, and greater than 1 is growth. So we're going to look at this in a little bit more detail. It starts off by saying, okay, now we're going to change our exponent, and instead of just x, it's now this exponent of t over p. So y is equal to a times b to the t over p, where y is your final amount, in contrast with a being your initial amount. B, the base, is your rate of growth. Growth if it's bigger than 1. Decay if it's in between 0 and 1. T ends up being your time. And that will be your input variable usually in our function. And then P ends up being your period growth. Period of growth and decay. How long it takes to go through one cycle of growth or one cycle of decay. All right. So in question number 1, we've got a culture of bacteria. It's going to double every 3 hours. We begin with 24,000. How many will be present in 5 hours? So this starts off with y is equal to, we know that 24,000 is your initial. Your rate of growth, it tells us that it is doubling every 3 hours. So we are going to be multiplying by 2 every 3 hours, which tells us that 3 hours is your period of doubling. X is your time over 3. Now, a lot of students sometimes get that mixed up a little bit, and you swap around the time and the period of this. But if you think about this, this will make sense. At 3 hours, when x is equal to 3, then this exponent will be 3 over 3. It'll be an exponent of 1, which means you're multiplying 24,000 times 2 one time. At 6 hours, that exponent will be 6 over 3. So you'll be multiplying 24,000 times 2 squared, which means it has doubled twice, which makes sense for 6 hours. So that kind of reasoning will help you remember which way this goes. How many bacteria will be present at 5 hours? So therefore, when x equals 5, this becomes y is equal to 24,000 2 to the 5/3, or y is equal to 76,195 bacteria. So kind of straightforward, not too bad. The only wrinkle is trying to keep that straight about what's going on in the exponent. Number 2, we've got half-life of plutonium. So maybe from science or from chemistry class, we know some things about half-life. You know that radioactive elements will deteriorate over a period of time. In this case, we have plutonium that has a half-life of 4 hours. If 60 grams was initially present, how much plutonium will be remaining at 7 hours? So we start off with y is equal to, your initial was 60 grams. Your rate is 1/2. We're talking about half-life. Its period of decay is 4 hours. So this ends up being x over 4. So that's going to be our function. Our first question is part A of this question is how much plutonium will be remaining after 7 hours. So after 7 hours, kind of straightforward, this ends up being 60 is equal to 1/2 to the 7 over 4. So this is y at 7 hours. Calculate this out to be 17.8 grams. 7 hours. The second part of this question is stating how many hours to the nearest hour till there's 2.65 grams remaining. So let's again start with y is equal to 60 over 4. For this part, we now know that we have 2.65 grams remaining. So 2.65 is equal to 60 times 1/2 the x over 4. So if we're going to do this algebraically, we're going to need logarithms because our unknown is in our exponent. Our first step is going to be to divide both sides by 60, and you have 2.65 over 60. I'd probably take that a step further and get your calculator to change that into a fraction. So as an exact value, 2.65 over 60 is 53 over 1200. That leaves me with, on the right side, 1/2 4. We swap this around into logarithm form. The base is 1/2, the base of our exponent. And so what we have is we have x over 4 is equal to logarithm 53 over 1200, base 1/2. X is equal to 4 times logarithm of 53 over 1200, base 1/2. Now at this point, you're either going to push this into your calculator just as it is, if your calculator can handle this. If your calculator can handle logarithms with different bases. If not, you need to do your change of base formula. And let's do log of 53 over 1200. You'll need to open brackets for that. And divide that by log 1/2. Either way, whether we do this in the previous step, if your calculator can handle that, or if we need to take this a step further, our answer for this ends up being 18 hours. All right, question number 3. The population of a town triples every 8 years. How many years until the population doubles? So y is equal to a is your initial value. We know we multiply by 3 every 8 years. So your base is 3, exponent is x over 8. How many years until the population doubles? We can do this a few different ways. You can assume that it starts with 100, we end up with 200. Think of it that way. You can think of it as if the population is a million, then it doubles to 2 million. But if you're wanting to do this algebraically, we could do this by calling this, if that's A, we end up with 2A eventually. 2A is equal to A times 3 to the x over 8. Notice that whether we started with a population of 100 or of 1,000 or of 1,000,000 and then growing to 2 million, regardless, in our next step, when we divide both sides by that initial amount, we end up with 2 on the left side. It's equal to 3 times 3 to the x over 8. We change this into logarithm form, and we have logarithm of 2 base of 3 is equal to x over 8. And x is equal to 8 times the logarithm of 2 base 3. When we calculate this out, we get x is equal to 5.05. And that's in years. Now we need to be careful with the wording of questions like this and the context that's going on. Because this question asks how many whole years until the population doubles. At exactly 5 years, the population hasn't doubled. And so you kind of need to be careful about this. Sometimes if we're talking about money that you're saving up, and so how many years until you have $10,000, you have a goal amount that you're having to save to, and it's maybe not, you don't have that amount at 5 years, it's maybe a little bit more like it is in this case. So you could make an argument, therefore, how many whole years until the population doubles? Therefore, it has doubled by the beginning. Doubled by the beginning of year 6. It has not yet doubled by the beginning of year 5, but it has now doubled at the beginning of year 6. How many whole years until the population doubles? It's not asking you to round to the nearest year, so we need to be careful about that. Question number 4. When we're talking about percentage growth or percentage decay, this will often be expressed as a percentage rate of 4.25% in this case. As a decimal, this is 0.0425. Now, if it is growing by that amount, then our rate of growth ends up being 1 plus that amount, is 1.0425. So if we multiply our initial amount by 1.0425, that will be your 4.25% growth. So this ends up being a very common thing that we're going to be looking at in this course is percentage growth and percentage decay. And that amount as a decimal, we will either add or subtract from 1. So in this case, we have y is equal to 42,500 is your initial, times 1.0425. And that's it. So what this ends up being is we have a table, y is equal to 1,000 times 1.5 to the x. So this is 1.50. We have an initial amount of 1,000. It's greater than 1, the base, so this is increasing. The rate of change as a percent, it is increasing 50%. This is 1 plus 0.50. Our initial amount in the second one, of course, is 300, but it is less than 1, so it is decreasing. What is your rate of change? If we take that b value of 0.8, if we take that b rate and subtract 1 from this, this might help see the pattern. And if we do b minus 1, so in this case, 1.50 minus 1 gives us 0.50. Multiply by 100, it's 50% increasing. b minus 1 in this case is 0.8 minus 1 is negative 0.2. This is decreasing 20%. It is going down at 20%. You're losing 20% of its value if your b is 0.8. This next function starts at 750 and is increasing because we have a b value of more than 1. If we take that 1.025 and subtract 1, we get positive 0.025. This is increasing 2.5%. And then our last one, decreasing, is 0.95. 0.95 minus 1 is negative 0.05. It is losing 5% of its value every year. So really it ends up being that how different is this from 1? How much above 1 or below 1 is that b value? And that will be a rate of increase or decrease as a percent. You multiply by 100. And that's it. All right. Part B to this. Compound interest is kind of a pretty regular type of application for exponential growth. And the idea is this, is the bank is going to pay you interest. You'll usually be given an interest rate. It says 6% slash A is quite common how it would be expressed. That means per annum in Latin, which means per year. Your interest rate will most always be expressed as an annual rate, even if they're not paying it out once per year. The idea is this: if we are compounding it annually, the bank is paying you interest just at the end of the year. And so you put in a deposit January 1st, you have this money in your bank account all year long, and then at December 31st, the bank will pay you interest on that. They will take 6% of your $1,000 and give you that. So to calculate this 6% interest, we're going to use 6% as a decimal. We get 0.06. If I take that 0.06 and multiply by 1,000, I get $60 of interest. That's how much interest that's paid into your account at the end of the year. So really what you have at the end of the year, you have $1,000 plus $60 is you have 1,060. But maybe the correct way to look at it is this. It's really 1,000 plus 1,000 times 0.06. That's where that calculation came from. And if I common factor 1,000 from that, this ends up being 1 plus 0.06. So we take 1,000 and we're going to multiply it by 1.06. That is your 6% of growth. After 2 years, what do you have? Well, you have 1,060 at the beginning of the year. You multiply that by 1.06 with 1123.60. But where did that 1,060 come from? It came from the previous year. We took 1,000 times 1.06. So that's my year one of interest times 1.06. That's my year two of interest. So that ends up being the same thing, 1123.60, which is what we have at the end of year two. So the idea is my initial amount times 1.06 squared gives me what we have in total at the end of 2 years. Similarly, we could do the same thing. We could, for 3 years, we could take our year two balance of 1123.60, multiply that by 1.06. But maybe a better way of doing it is taking $1,000 times 1.06 for 3 years. We're going to use our exponent. It's going to count how many years of growth we've had. And our B value ends up being that initial amount plus your 6% interest, so 1.06 as our multiplier. And we end up with, after 3 years, 1191.02. It's like we've made a formula for after 2 years, we have 1,000 times 1.06 to the T. So that ends up being very useful to look at our interest that way. Is compounding interest is we're adding 6% into our account, so it's 0.06. We add that to 1 and call it 1.06 is what we're just going to multiply. Instead of having to calculate your interest after every year, add that in and then recalculate it, ends up being a lot slicker a process. Now, the reality is most banks aren't going to pay you interest just once at the end of the year. So if you make your deposit on January 1st and at the end of the year, at the end of 1 year, December 31st, you would get paid your 6%. But if your bank wants to, allows you to be paid semi-annually. Semi means half, so that's every half a year. So what they're going to do is on July 1st, they're going to pay you. Now, do you get all 6%? On July 1st? No, because 6% is your annual interest rate. So what they're going to do is they're going to pay you 3% on July 1st, 3% on December 31st. And so what this ends up looking like is for your year, 1 year of interest in your account, you have 1,000 times 1.03. That would give you your balance after 6 months is 1,030. And if you took that and multiplied by 1.03, that would be your end of the year balance is 1,060 and 90 cents. So notice that it went up by $30 in the first 6 months, but in the second 6 months, it grew slightly more because you're getting interest on interest. This also ends up being slightly more than it was if you were just compounding it at the end of the year. In the first part of this question, it was 1,060 exactly at the end of the year. Now you've earned a tiny bit more. Over long periods of time, this tiny bit more will add up because you'll continue getting interest on interest. And you know what the exponential growth curve looks like. It starts off slowly, and then eventually it starts getting steeper and steeper. And so that's what's going to be happening with money. And so over a short amount of time, it has a little bit of an effect, but over longer periods of times, it has more effect. Now, is this how we're really going to use this calculation? Probably not. Probably what we want to do is take your $1,000 and get your 3% twice. And we calculate that 1,000 times 1.03 squared is equal to 1,060.90. So at the end of 2 years, we have $1,000. So let's start to use this slicker tool. And $1,000, how many times have we compounded? By the end of 2 years, we have had 4 compounding periods because it was compounding twice per year. So it ends up being 1,000 times 1.03 to the 4. And we end up with 1125. At the end of 3 years, we could either take our answer from here and multiply it by 1.03 2 more times, or we could just take $1,000, your initial 6 periods of interest, 6 compoundings of interest, ends up being 1194, 105, 1,000 times 1.03. Now, if we have t years have gone by, and if we have had 2 compoundings every year, then that means this will be to the 2t. Remember that this was 6% per annum, but if we were compound, so 0.06, but if we were compounding it twice per year, we ended up with 3% every 6 months. So it's kind of like what we've done here is we've taken 1 plus 0.06, and we divided it by 2. That gave us our 1.03. What would our formula look like if the investment was compounded quarterly? Quarterly means 4 times per year. It means every 3 months, but 4 times in a year. What it would look like for quarterly would be y is equal to 1,000. I suppose let's start to use a is equal to 1,000 times what are we going to have quarterly? We're going to have your 0.06, we're going to add that to 1.06, we're going to divide that by 4, because you don't get 6% every quarter, every 3 months. We have to divide that by 4. When we divided by 2, that was 3%. So this ends up being 1.5% that you're going to get every quarter. And our exponent ends up being 4t. Because when t is 1 for 1 year, this will be 4 times 1. 4 quarters, 4 compounds of interest, 4 compoundings. If we have monthly interest, if our interest is happening monthly, this ends up being A is equal to 1,000 times 1 plus 0.06, but we're going to divide it by 12 because we're going to get 1/12 of that 6% every single month. So we're going to get about we're going to get a 0.5% each month. Our exponent will be 12t. 1,000 times 1.005 to the 12t. 0.5% growth every month. So this ends up being our formula for compound interest. It shows up a lot of places in obviously in finance, but it ends up being a pretty useful idea. This is not on your formula sheet, but it's a pretty decent thing to understand and get your head around how compound interest ends up working. And so what we have here is A, it's your final amount. When P is your principal amount. Principal is what we use in finance circles to talk about your initial amount. It's called your principal. R is your annual interest rate. As a decimal. Don't forget to convert your percent to a decimal. N is your number of compounding periods per year. Of compounding periods per year, and T is your number of years. So throw that all together. You invest $2,300, earning 6% per annum interest, compounded monthly for 7 years. How much money do you earn? So A is equal to P 1 plus R over N to NT. 2,300 is your principal. 1 plus 0.06 is your rate as a decimal. We are compounding monthly, so this is divided by 12. So 12t. This ends up being equal to 2,300. 2,300 times 1.005 to the 12 times 7. We push this through our calculator. We get 3,496.85. Now, a couple things to be careful about. This base is super sensitive to rounding. So if there's rounding to be had, write down enough decimal places write down a significant number of decimal places, but don't use your calculation based off of your rounded amount. Take your actual interest rate, divide it by your number of compoundings. If you're compounding it daily, it's going to be 0.06 divided by 365. Then add 1, and then use that sitting there in your calculator as your base to do your actual calculations. Don't round it off and then use that rounded amount with your calculations. And then our last one, how many years to the nearest tenth to triple this investment? So A is equal to 2300, 1.005, 12, and we've tripled our investment. Notice that it doesn't matter when we divide both sides by 2300. It doesn't matter how much we started with. You may have started with 2,300 in your account. You may have started with 10,000 in your account. It's not going to matter. To answer this question, how long does it take for you to triple your investment? So we end up with 3 is equal to 1.005 to 12t. Swap this around into log form. We end up with 12t is equal to the logarithm of 3 with a base of 1.005. T is equal to logarithm of 3 base 1.005 over 12. And again, if your calculator can handle where you change the base, that's fine. If not, what you might have to do is t is equal to log 3 divided by log 0.005 and use base 10 logarithms. And then also in the denominator is 12. So as an exact value, log 3 over 12 log 1.005. Be careful when you do this calculation that you have brackets around this, and you end up with t is equal to 18.35. It asks how many years to the nearest tenth, so t is equal to 18.4 years. All right. Good luck, and again, if you have any questions, please let me know.